In this example, we're analyzing Mars' orbit around the Sun. We're given that the mass of the Sun is 2.0 times 10 to the 30 kilograms. The radius of Mars' orbit is 2.3 times 10 to the 11 meters, and the universal gravitational constant is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. And the question is, what's the speed of Mars as it travels around the Sun? Now, the key to analyzing the orbit of any planet, or any satellite for that matter, is to understand that in order to travel in its orbit, the planet or the satellite must experience a centripetal force. And that centripetal force is supplied by the gravitational attraction between the planet and what it's orbiting. So in this case, the centripetal force is given by the gravitational attraction between Mars and the Sun. Well, since this is the case, we can say that the gravitational force equals the centripetal force. After all, if the gravitational force is the centripetal force, then gravitational force and centripetal force equal one another. Well, we have equations for both the gravitational force and the centripetal force, so let's put them in there. The gravitational force is the gravitational constant times the mass of one object, Mars, times the mass of the other object, the Sun, divided by the radius squared of the circle. The centripetal force is the mass of the thing that's moving around, in this case Mars, times the speed squared, divided once again by the radius of the circle. So now we've built an equation that relates the characteristics of the Sun to characteristics of Mars as well as the radius of Mars' orbit. Now notice what happens here. The mass of Mars cancels. Since we're trying to figure out speed, we might as well solve for v squared by multiplying both sides by r. And we find out that the gravitational constant times the mass of the Sun over r equals v squared. That's a pretty important equation, so we're going to save it. All right, now think about what this equation means. V is the speed of the thing that's orbiting. That's Mars. Look at what's on the left-hand side of the equation. A constant, g, the mass of the Sun, and the radius of Mars' orbit. So notice that the speed at which Mars is traveling doesn't depend on the mass of Mars. In general, that means the speed of a planet or the speed of a satellite doesn't depend on the mass of the planet or satellite. It only depends on the mass of the thing that it's orbiting. In this case, the speed of Mars doesn't depend on the mass of Mars, only the mass of what it's orbiting, the Sun. Well, we know everything in this equation except v, so we can solve for the speed. V squared is g, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared, times the mass of the Sun, 2.0 times 10 to the 30 kilograms, divided by r, the radius of Mars' orbit, 2.3 times 10 to the 11 meters. Now it's worthwhile to see how the units cancel here. Remember that a Newton is a kilogram meter per second squared. Now look at the units. I've got kilograms and kilograms divided by kilograms squared, so those cancel. One of the meters cancels as well because I've got a meter on the top and a meter on the bottom. We're left then with meters squared over seconds squared. Well, that's good because we're looking at v squared right now. Since v is meters per second, v squared ought to be meters squared per second squared. So the units work fine here. When we take the square root of both sides, the numbers work out to 2.4 times 10 to the fourth, and the units work out to meters per second. So that's the speed of Mars as it travels around its orbit. The second question in this example just builds on the first, so we'll do it here. Remember, the speed of Mars in its orbit is 2.4 times 10 to the fourth meters per second. We just determined that. We are already given that the radius of Mars' orbit is 2.3 times 10 to the 11 meters, and the question is, what's its period? How long does it take Mars to make one orbit? Well, we're given the radius of the orbit, so we can determine the distance around it. The circumference of a circle is just 2 pi r, so the circumference of this circle is 2 times pi times 2.3 times 10 to the 11 meters. That's 1.4 times 10 to the 12 meters. Now to determine the time, we'll just go back to our old friend, distance equals rate times time. But this time we're looking for time, so let's divide both sides by rate. So the time is the distance divided by rate. We know the distance, we just calculated it, 1.4 times 10 to the 12 meters. We also know the rate, that's the speed, 2.4 times 10 to the 4 meters per second. Meters cancel, and the second that's in the bottom of the fraction comes up to the top, and we find out that the time is 5.8 times 10 to the 7th seconds. That turns into 1.8 years. So it takes Mars almost twice as long as it takes the Earth to make one trip around the Sun.